Hey guys, Mr. McKinney here, reviewing our Unit 1, Limits and Continuity, which is very closely aligned to the AP Unit 1, which is one of the units you'll be working on this week. First thing we covered was limits. We looked at graphs. Limits are what the function approaches, not what the function actually is as x approaches a given value. So all three of these functions have the same limit. The limit would be 2 as x is approaching 1. Whether the function is defined there or not, that limit is still at 2. In order for a limit to exist, both of the one-sided limits have to be the same. If you see a little negative here, that means the limit coming from the left side. On this problem, that would be 2. If you see a plus here, that means the limit coming from the right side. On this problem, that would be -1. Another example of one-sided limits has to do with vertical asymptotes. So if we think about these two rational functions, 1 over x minus 5 and 1 over x minus 5 squared. And this is something that the AP evaluates a little bit differently than the way I taught it in class. So I'm going to go ahead and show you what the one-sided limits and the graphs look like for these two and then talk about them a little bit. So the limit as x approaches 5 of 1 over x minus 5 would have a vertical asymptote at 5. As we approach 5 from the left, we're going to -infinity. As we approach 5 from the right, we're going to positive infinity. Since -infinity and positive infinity are not the same, the overall limit does not exist. Over here, since I've squared it, both sides are going to go to positive infinity. So the limit as x approaches 5 from the left and the limit as x approaches 5 from the right are both positive infinity. In class this year, I said that that limit was positive infinity, but the AP exam only considers finite limits in this case. So we'd want to say that this limit does not exist, even though they're both positive infinity. The limit properties basically just say that you can add, subtract, multiply, and divide limits as long as each of those limits are real numbers and the value that you're approaching is a real number, and if you have a scalar, that's a real number as well. I put this function up so that you guys could think back to the difference between a function value and the limit value. If you have questions on any part of this graph, email myself or Mr. Jansen's. Average rate of change is always going to be a slope calculation. It's always the slope of the secant line. So they're going to ask you an average rate of change over a time interval. Just take the starting time and the ending time, plug those two values in to get your function values, and then set up a slope calculation. So whenever you see average rate of change, that's always going to be a slope calculation. If you see instantaneous rate of change, or it asks for the exact value, then you're going to have to use this limit calculation. The limit as h approaches 0 of f of x plus h minus f of x over h. Basically, you're taking the slope between 2 points as they get infinitely close together. The distance between them goes to 0. So let's think about a distance being modeled by y equals 16t squared minus 10t. To find the exact velocity, the exact rate of change, I'm going to need to use the limit formula. So I'm going to take the limit as h approaches 0 of f of x plus h minus f of x. Now, this problem would take a while, so I've worked the whole thing out for you here. Keep in mind that you need this limit statement until you're not dividing 0 by 0. So at this step, I could cancel out an h on the top with this h on the bottom. Now I'm allowed to plug in h is 0. 16 times 0 goes away. Once that part's gone, now I don't have to write limit anymore. To figure out the exact velocity at 3 seconds, I would simply plug in 3 seconds into this formula and get 86 feet per second. Many times on the AP Calculus exam, when you try to evaluate the limit, it's going to evaluate to 0 over 0, which is considered indeterminate form. We've learned L'Hopital's rule, but at this point in the course we hadn't yet, so there were some algebra tricks. I'm not going to go through all of these, but there's worked out slides that kind of go over them. One thing we talked about was how to factor the sum or difference of cubes. So you could factor x cubed minus 27 and then end up factoring out x minus 3. Another thing was synthetic division. So you would divide the top by the bottom, and there's some tricks with synthetic division that you would use. I'll show how to set it up real quick. Basically, you make your box, you start with your coefficient, 1x to the 5th, 0x to the 4th, 0x to the 3rd, 0x squared, 0x, and then my constant of negative 243. Whatever number is here, you put the opposite out front. First number comes down, then I multiply, then I add, multiply, add, multiply, and so on. If I divide this out, you're going to end up getting x to the 4th plus 3x cubed plus 9x squared plus 27x plus 81. Now I can plug in the 3. I would have had a factor of x minus 3 in front of this, but that's what's going to cancel out. If you have a square root that you're trying to get rid of, one way that you can do that is with the conjugate. So the conjugate of the square root of x plus 1 minus 1 would be the square root of x plus 1 plus 1. So I'd multiply that on the top and the bottom. Again, I've got it all worked out here. The last thing was just adding together fractions that don't have the same denominator. You can use fast adding, or you can just add together with the lowest common denominator. Fast adding just means you don't get the lowest common denominator. You do 4 times 1, you do 4 plus x times 1, and then you just use both of those as your denominator. I've got it worked out here. A big focus on the AP exam is the characteristics of rational functions. So knowing when there's going to be asymptotes, knowing where the intercepts are going to be, knowing where there's going to be discontinuities. So make sure you know the rules for horizontal and slant asymptotes. The pre-cal teachers teach them a variety of ways. Just make sure you've learned them either with one of the acronyms or just by memorizing the rules. Whenever the denominator or the bottom of a fraction is 0, there's going to be some sort of discontinuity. If you can cancel that factor out, it's a removable discontinuity called a hole. If you cannot cancel that factor out, it's going to give you a vertical asymptote or a non-removable discontinuity. Anytime you want to find an intercept, just set the other value equal to 0. For the y-intercept, x equals 0. For the x-intercept, y would be 0, which is going to be when the numerator is 0. So for this problem, I would want to factor it first, see what cancels out. I recommend that you guys hit pause, try to do that, think about what all the characteristics are. All right, hopefully you had a chance to do that. You can factor the top and the bottom. I could factor out x plus 3, so that's going to give me a hole at x equals negative 3. That hole would be at negative 3, 1. You're not going to be able to see it on any graphing utility, but there's a hole right there. X-intercept would be at 0.50. Y-intercept would be at 0.25. If all the x's were 0, 3 over 12 would be 1/4. You have a horizontal asymptote at 2 because the exponent's the same. So I'm just dividing the number in front of the x's. Next thing I want to talk about is the definition for continuity. The definition for continuity has 3 parts. First of all, the function has to exist at C. Second, the limit has to exist at C. And most importantly, the limit and the function must be equal to each other. Mathematically, it would be written like this. If it's not continuous, then we would say there's a discontinuity at that x value. If the limit exists and it's a finite limit, that's going to give you a removable discontinuity, also called a hole. If you have a vertical asymptote, then you're going to have an infinite discontinuity. If there's a finite distance between the left limit and the right limit, that's a jump discontinuity. So if we look back here, we've got a jump discontinuity here. We've got a removable discontinuity here. We've got an infinite discontinuity here. Both infinite and jump are considered to be non-removable. The hole is removable. To think about what interval it would be continuous on, basically you just look for discontinuity. So this would be continuous from negative infinity until b, and then in between b and c on an open interval, in between c and d on an open interval, in between d and e on an open interval, and then e to positive infinity. The last thing I want to talk about is 2 theorems. The first one is IVT, or the intermediate value theorem. This is the easiest one in my opinion. As long as f of x is continuous between a and b, and f of c is between f of a and f of b, then there is a number c between a and b. Basically, I like to think about it like this. Let's draw a little function. So here's a, here's b, here's f of a, and here's f of b. So we're going from a to b, from this value to this value. I don't know how I'm getting here. I just know that I'm continuous as I get from here to here. If f of c is between these two, so f of c is here, then there must be some value at which the function hits that number. So if I get from here to here, I have to hit every number in between. Why don't you guys read this problem, hit pause, and then try to answer which of these four things must be true and which of these four things could be true. So again, hit pause. All right, let's see how you guys did. So I'm going between 0 and 5. The y values are going between 10 and 20, which means that in between 0 and 5, the y values are going to hit everything between 10 and 20. So at some point, the function is going to hit 15. This is guaranteed to be true. At some point, could the function equal 5? It could be true, but it doesn't have to be true. This is saying halfway through, you're at half of the height. That could be true, but you're definitely not guaranteed to have that be true. And then the last one is that the derivative would equal 2 for some c on 0 to 5. Now that actually isn't IVT, that would be MVT, and I was curious how many of you guys got tricked. That could be true, but MVT requires that you have differentiability as well. So the only one that must be true is A. Now here's a little bonus. Here is one of the only new things that you're going to have to learn over the next month and a half. It's called the squeeze theorem. Some teachers will call it the pinching theorem or the sandwich rule. I barely, if at all, taught this last year because it almost never shows up on the AP exam. And then last year it showed up. So be careful, it might be there. Basically, if g of x is less than or equal to f of x is less than or equal to h of x, so f is always bigger than g, but less than h, for all x values near c. And at c, the limit as x approaches c of g is equal to L, and the limit as x approaches c of h is equal to L, then the one in between them, f, must also be L. So the limit as x approaches c of f of x is also L. Visually, this is a lot easier to understand. So g is less than f is less than h. So for example, on this first picture, h is always on top, g is always on the bottom. When we're looking at a right here, the limit of h and the limit of g are both at the same y value. Since f is always in between those two, the limit as x approaches a of f of x must equal whatever both of these other limits were. So the limit as x approaches a of h of x, which is also going to equal the limit as x approaches a of g of x. Now this only works if f is always in between g and h. A lot of times you'll see it where you have some sort of sinusoidal function that's bouncing up and down, but as long as it's always less than this function and greater than this function, and both of these functions were equal to 0 here at 0, then you know the limit of this function that's oscillating back and forth is also 0. I hope this quick review was helpful for you guys. Please reach out to myself and Mr. Jansen if you guys have any questions as you work through the AP classroom assignments. Thanks and good luck.